In our earlier videos for this chapter, we took a look at a couple of different acid-base reactions. Now I want you to consider one that looks maybe a little different from the others. And in that reaction, we're going to take nitric acid, which is HNO3, and we are going to react that with a strong base like, let's say, potassium hydroxide. Okay. Now, the product for this reaction is going to be water plus potassium nitrate. Okay, now what I'm going to do is I'm going to look at this a little bit differently. I'm going to look at it in terms of an ionic equation. Okay, we talked about this a couple chapters ago, where the HNO3 can be broken up into H plus nitrate plus K plus OH minus, which gives us water plus K plus nitrate. And if you remember, when we're looking at an ionic equation, we can look at the things that are not changing from the left side of the equation to the right side. So in other words, potassium and nitrate do not undergo any changes, and therefore they are spectator ions. So what we're left with is H plus hydroxide giving water. Now, if you think about it, it doesn't matter what strong acid I started off with, because every strong acid is going to completely dissociate to produce protons in solution. The same thing goes for hydroxide. Any strong base is going to produce hydroxide. Okay, so what this is telling us is that any reaction of a strong acid with a strong base is going to behave just like this net ionic equation that's shown that we're looking at right now. And when you think about it, we have an acid, okay, which is something that's going to have a low pH, and we have a hydroxide, which is a base, which is going to have a very high pH. And when they come together, we get pure water. And the only source of hydronium at that point would be from the autoionization. So the pH would be equal to 7.0, okay, which is neutral, and that's why we call this a neutralization reaction. Now, there are some acids out there that are capable of giving up more than one proton. We call those polyprotic acids. Okay, so when you think about something like HCl, HCl can only conceivably give up one proton. Okay, so we say that HCl is monoprotic, whereas sulfuric acid would be diprotic. Okay, and phosphoric acid would be triprotic. And of course, we can have more. We could have 4 or 5 or 6, but usually when we have more than 3, we just start to refer to them as being polyprotic. Now, the way that these things are going to behave in the presence of bases are going to be slightly different. Okay, if you think about it, if I take HCl and I react that with sodium hydroxide, I get a molecule of water plus sodium chloride. But if I take a diprotic acid like sulfuric acid and I react that with sodium hydroxide, I now have two protons that have to be removed, which means I need to have two sodium hydroxides, and that'll produce 2 moles of water plus sodium sulfate. Okay, if we have a triprotic acid like phosphoric acid, it's going to require 3 moles of the base, producing 3 moles of the water, plus Na3PO4, sodium phosphate. Now, one thing that we have to be careful of is that we can't simply count the number of protons that are on a molecule and assume that every one of those is going to be acidic. A great example of this is acetic acid. Okay, this is the same stuff that's in vinegar. In fact, vinegar is about a 3 to 5% solution of acetic acid in water. Now, acetic acid has a chemical formula of C2H4O2. And taking this at face value, we might assume that there's going to be 4 acidic protons. But it turns out that that's not the case. If we were to look at the Lewis structure for acetic acid, what we would find is that 3 of the hydrogens are attached to a carbon, and 1 of them is attached to an oxygen. Okay, so there are 3 of one type and 1 of another. Now, the theoretical basis for why it is that some are going to be acidic and some are not, well, that's a conversation that we would have in organic chemistry. But for right now, for our purposes, you're just going to have to kind of take my word for it that of the 4 protons, only that one is going to be acidic. Okay, and for that reason, despite having 4 protons, acetic acid is still a monoprotic acid. Okay, now the last topic that we need to address in this chapter is the concept of what we call buffer solutions or buffer systems. And buffer systems are interesting and very important parts of nature. In fact, without buffer systems, we would not have life as we know it. Every buffer system is composed of the same 2 things: a weak acid plus its conjugate base. Okay, so let's think of a weak acid. We know that there are 6 strong acids, so that's HI, HBr, HCl, HNO3, H2SO4, and HClO4. So if we just pick an acid aside from those, let's say we go with something like HF. Okay, its conjugate base, well, if we think about it, the conjugate base is going to be 1 proton shy of the acid, so 1 less proton, and 1 negative charge more. So HF is neutral, so we remove 1 proton, and what we're left with is going to be F minus. Okay, now I can't just buy F minus in a jar. I can't just go to the store and get that. In order for me to get an anion, it has to be attached to a cation. So we're going to say that the fluoride is going to come in the form of sodium fluoride, but knowing full and well that the sodium fluoride, once it hits water, is going to completely ionize. Okay, so if we have a weak acid and its conjugate base, we have what's called a buffer system. Now, the thing we need to remember is what a buffer system does. And what it does is it resists change to pH. Okay, and this is huge. Okay, if you think about this, think about all the foods that you eat that are acidic. Okay, things like orange juice or lemonade. Can you imagine if, upon drinking those things, that your body's pH would just plummet down to like 1 or 2? Well, your body would stop working. Your proteins in your body depend upon a very carefully balanced pH. So we have a buffer system in place. Now, it's not an HF and fluoride buffer system. In fact, it's usually based on phosphate. Let me actually change this. Okay, so we have a weak acid and its conjugate base here. And this keeps us centered right around 7-ish. Okay, we're not going to worry about the exact numbers right now. But what we need to be able to do is to recognize whether or not a system qualifies as a buffer system. Okay, so we have to look at it to see if it's a weak acid with its conjugate base. Now, here are some examples of things that are not buffer systems. For example, we could have HCl combined with sodium chloride. Now, HCl is an acid, but it's not a weak acid. Okay, it's strong. Now, Cl minus is the conjugate base, but again, it's the conjugate base of a strong acid, which means this is not a buffer. Okay. Okay, now, what if we had something like HF plus sodium bromide? Well, HF is a weak acid, so that's a good start. Okay, but bromide is not the conjugate base of HF. So again, this is not a buffer. But if we had something like ammonium, which is a weak acid, and we have that combined with ammonia, okay, then we do have a buffer. So let's examine this a little bit more closely. Okay, we have the weak acid, and we have to examine NH3 to see, is this the conjugate base of ammonium? Well, ammonium has 4 hydrogens. We knock one of them off, we get down to NH3. It had a positive charge. It's going to become one step more negative, so one step more negative than +1 is going to be 0. So again, this qualifies as a buffer system. Okay, and what we have here is, again, it's a fairly complex system, but it's also a very elegant system, because if you have a mixture of a weak acid and its conjugate base, like for example, let's say we have this ammonium and ammonia. Okay, so let's say we have an acid coming in and it reacts with this buffer solution. It would react with the ammonia that's laying around, producing ammonium, okay, which is not nearly as acidic as hydronium. Okay, and if we had hydroxide that was added to it, that would react with the ammonium, okay, to produce ammonia. Okay, and in the course of this whole process here, we have an equilibrium going on in the background. Okay, and what's happening here is when we react with acid, we're going to be building up the amount of ammonium, which is going to drive the equilibrium to the right, which is going to balance things out a little bit better. Okay, and if I were to add hydroxide, that's going to increase the amount of ammonia, which is going to drive us to the left, again balancing things out. Now that's not the most important part here, but that is the theoretical basis behind it. So keep in mind that a buffer system is composed of a weak acid and its conjugate base, and that its whole role in any system is to resist change in pH.